So the talk will be about device characterization in this era of technological advancement. And let me see. All right. So we've been seeing a lot of development in all the semiconductor technologies, going from the 1G to the 6G with a lot of requirements. But I wanted to show the relation of this requirement to our industry, which is when our customers or our partners are coming to us, they want higher frequency, higher power, higher efficiency, higher accuracy, higher speed. In fact, they want it all. Oh, I see question that the presentation is blank. Do you still see my
We can see the screen.
Perfect.
At least I can see the screen. So I think that is a problem of the user.
Okay, sorry. Okay, so the idea here is we get all these requests, and of course, it has to be low cost. Now, the problem is we are in this industry and working with a lot of partners, and we are learning a lot from them because every time they get a new idea, it drives us actually to develop a new instrument or a new method for measurements. So let's go to the motivation for load pool. So we've been using load pool for a long time, but one thing I wanted to highlight is the capabilities of the measurements on a device, especially a non-50 ohm device, a transistor that is highly dependent on its load impedance, can generate, it's nonlinear, it can generate harmonics, can generate frequency mixing. So the measurement on a VNA, for example, would characterize that DUT to a certain extent, but it cannot actually characterize that DUT with all the non-linearities and non-linear capabilities or characteristics. And for that, we need to do a power test where we are using a load impedance and measuring with a power meter, for example, at the output of the DUT. And with that, we are able to extract all the contours for maximum efficiency and maximum power and so on. So this is very briefly the load pool explained in a few seconds. But it has more to it. First of all, you need an impedance tuner. An impedance tuner is a quite simple apparatus where you have a transmission line with a probe. By moving the probe on the y-axis, you change from 50 ohm to a certain gamma. And by moving the X, you are moving the phase. So you are able to tune on the Smith chart. However, one thing that is important is, imagine the first setup that I showed in the previous slide, where we are measuring at the power meter reference plane. We are moving on the black curve here. And what we see here on the this is the tuner loss. And when we reach a certain maximum, then we just stop there. We measure, we take the loss in account, and then we say our device has a certain power. But in fact, the loss is not linear. And the loss can at a certain time be faster than the output power of the DUT. So that's why what we need is to be able to measure the power meter, but at the tuner, at the DUT reference plane. And for that, the key point is we need to pre-calibrate the tuner. So it does not matter if the tuner is automatic or not. It needs to be pre-calibrated. An automatic tuner is easily pre-calibrated, of course, than a manual tuner. But the point is pre-calibrated. And with that, we are able to characterize in real time the device at the DUT reference plane. This brings the accuracy part of it. Of course, our customers every year are looking to and are fighting actually for these 2-3% efficiency and want to be more efficient. So with that, along the years, there are a lot of developments. And one of them, for example, is the harmonic tuning using cascaded tuners or tuners with triplexers, or the what we call the multi-harmonic tuner, where we have one structure that controls the 3 harmonics independently. So you are able to tune everywhere you want on the Smith chart for the 3 harmonics. Now, for power measurements for a long time, they were using what we call a scalar setup, using power meters, spectrum analyzer, and so on. The problem with this technique, well, at that time, that's what we had. So we could characterize the device. But the problem with the technique is it has limited characterization of the DUT. For example, we cannot measure the P in delivered. We cannot measure PAE, where we cannot measure the gamma in of the DUT or the power gain. And one thing that is important, it relies on the accuracy of the tuner calibration. Okay, and what does that mean? It means that if we make a small error on the S parameter of the tuner, we're going to make a large error on the power characterization, especially when we are at a high gamma, because the loss of a tuner is 1 minus S11 square over S21 square. And the limit of this function goes towards 0 over 0 if we go to high gamma, which means that a very slight error in the S parameters gets a huge error in the loss of the tuner. So to increase the accuracy, we moved to the VNA-based load pool, or the vector receiver load pool. This technique also existed for a long time, but at that time, the system was very much complex, using synthesizers, test sets, triggering all this together. The couplers were very lossy, so we were losing tuning range of the system. With the new VNAs that have, actually we can build that system using one instrument, using a VNA, with having access to the receivers, using the sources from the VNA. And we can even, we have some VNAs that has more than one source. So with that, measuring the A and B waves, we are able then to characterize as we did for the scalar, but with the fact that we are able to measure the P in delivered, the power gain, the PAE, the gamma in. And if you look at in this setup, I omit actually to put the source tuner, which is, it was done intentionally, because as we are measuring the gamma in of the DUT in real time, we don't in fact need a tuner to tune the input of the device. Because the information needed in terms of gamma in, it can be obtained in real time. The input tuner is used only when we have a high power device and a big mismatch between the 50 ohm and the input of the device. So we put the tuner here as a pre-match to reduce the need for power when we are characterizing the device. Another thing that this technique or this structure of setup helped us doing is what we call the waveform engineering. As we can characterize this transistor in amplitude and phase, and with the harmonics, we are able to work on the waveform. So it's not anymore a quantitative evaluation of the device, but more of a qualitative. So we are able to go reach those class of operation that we were not able to even assess with the scalar load pool. But with this setup, we are able to put ourselves in the class of operation that are desired. Now, when we're talking about passive tuners or mechanical tuners, we cannot go without talking about the tuning range. So these tuners are passive, so they are inherently lossy. And by being lossy, we reduce the tuning range, of course. If we add to that the couplers, the cables, the probe tips, if we are on wafer, this tuning range gets smaller and smaller. And as we know, devices need to, if we want to go and characterize devices, especially at high frequency, like in this case at 28 gigahertz, we want to reach high gamma, then it becomes more challenging. So for that, we have what we call the active load pool. And the active load pool uses an open loop here that has a source with phase and amplitude control. We have a power amplifier to drive the signal, and then we inject the signal. So the way it works is, as we are measuring with the wave, we are measuring the B2 wave coming out of the DUT. We are able to synthesize an A2 wave coming out of the second source of the VNA, for example, to the output of the DUT to synthesize the gamma load. The gamma load being A2 over B2. So I'm able with that to synthesize any impedance on the Smith chart, as long as I have a power amplifier that is capable of injecting the signal. Of course, when we are dealing with high power devices, and again, coming back to the first slide, high power, high frequency, high accuracy, high efficiency. So all this comes together. Well, if I am dealing with high power devices, then the power amplifier by itself is sometimes not enough. So we can go to a hybrid solution where we are putting a tuner, and this tuner will have, in this case, the same functionality as the source tuner, where the source tuner is used to reduce the need for power to drive the device. Well, here this tuner will be used to reduce the power needed to active inject the device. So the active injection will be reduced, and this tuner helps in that. And that's what we call a hybrid active solution. Nowadays, we also see a lot of requests for very high frequency measurements, and there are solutions. And as you can see, the systems, the device characterization setups gets more and more complicated, more and more important. So in this case, we are using a VNA with frequency extenders in a waveguide setup, and using an IQ modulator to generate the signal, multiplying the frequency of the signal to go to the RF frequency required. We have step attenuators to change to sweep the power. Then, of course, we drive the power, we inject through a source tuner that is a waveguide tuner in this case, and not a coaxial tuner, because all the solutions we talked about in the beginning were coaxial. Here we are in a waveguide, and we can see that we are developing new solutions to address this type of capabilities. And in this case, we are showing a 1 watt device at 94 gigahertz. This is a paper that was published lately. We can also address customers going up to 250 gigahertz, and this is a request that is higher frequencies is there. So with the D band, the G band, all the new band that we need to address. In fact, we wouldn't be surprised to go up to 1.1 terahertz. Solutions are already there, ideas are already there, and we are working toward those type of solutions. I'm trying to go as fast to cover some time here, so sorry if I go too fast. Another requirement that we see is in terms of the bandwidth. So if you see the evolution of the bandwidth from the era of the WCDMA, which was 5 megahertz, we are now addressing requests at higher frequency for the FR2 up to almost 1 gigahertz of bandwidth. And these requirements using a passive tuner starts having some limitations, and limitations are seen here. So if, for example, we have a structure like this, when we have a passive tuner with on wafer, for example, if we use this tuner, this is the frequency response in blue. You see the frequency response of the tuner depending on the bandwidth. So for the WCDMA, the bandwidth response of the tuner will be here, and we can see the response at the tuner reference plane for a 5G. But if we move this reference plane to the probe tip, we increase the length from the tuning reference plane to the duty reference plane, and then we can see that the skew of the phase is even larger. And with that, we can see that a tuner needs to be changed in a way to reduce, in fact, this length. And a lot of in the industry, a lot of solutions are there with very miniaturized tuners that goes directly from the tuner, connected directly to the probe tip to reduce all this length here and reduce the skew. But another solution that also exists based on the active load pool is the generation of a wideband signal at the input of the DOT, and then what we do is we get the output, we measure the output power or the output signal, and we mimic the output signal through an injection using AWGs, and we condition this signal with different amplitude and phase for different tones. And with that, we are able to synthesize an impedance over the bandwidth in the impedance we want. So in other words, we could, for example, decide to have one impedance, a fixed impedance, one dot on the Smith chart for the whole bandwidth, or we can have a profile of an impedance. Like imagine we have an antenna, so we can measure an antenna and we can synthesize this, the gamma of this antenna, the impedance of the antenna directly on this this instrument to be able to present that load exactly to the DUT. The structure of such a system requires, of course, AWGs to be able to generate the signal. We were able to synthesize impedances at the input and at the output at the harmonics, as well as at the fundamental. Another aspect is we can also, and this is some of the requirements from customers, is to tune the baseband of the signal to increase the linearity. So these are some of the results. I'm going to skip that. So in fact, what we are doing is by tuning on a wider band, we are able actually to synthesize the impedance needed, so on the full bandwidth, and have the shape of the signal at the output. Well, if we don't do that and we are just synthesizing an impedance at one frequency with the phase skew, then we change actually the gain with the frequency, and this is the type of results we get. The last is actually about the baseband tuning, where we synthesize impedances at the baseband to be able to reduce the adjacent channels power. So with that, we can increase the linearity, or study actually the linearity of that device. So in conclusion, as we see the evolution of all the technologies, we can see also the evolutions of the tools. And these tools are developed with the help of our customers. So please don't stop requesting new tools, because that's what drives our industry, drives our engineers and our development toward new methods. Thank you very much.